Hey guys, I just want to take you through a quick look at Kirchhoff's law, and we're going to be using test yourself question number 25 for this quick exercise. So we have this circuit here, and we'll get into my markup there in a second. But first, the circuit has an EMF of 3.0 volts, and the lower cell has an EMF of 2.0 volts. Both cells have negligible internal resistance, which is important, and is a common thread in the setup of these kinds of problems. But we need to calculate the readings of the two ammeters and the potential difference across each resistor. Now, when you look at this, you might think that this problem is more difficult than it actually is, okay? But Kirchhoff's law for voltage and current actually make it fairly straightforward. So let's talk about it. First, we need to set up two loops here. The first loop is loop 1, and the direction of the loop doesn't actually matter, but you should try to be consistent. So I've been consistent here by setting up my loop from positive to negative, but if you want to do it a different way, that's fine. The only time it's going to make a difference is sometimes you might end up with negative voltages in some components or negative currents, and I wouldn't worry about it too much. Okay, so there's loop 1 and loop 2. So we start the loop at my power supply, and this is always going to be a positive voltage. And then if we measure the voltage as we go around the loop, the first component we come to is resistor 1. So I would normally just call this voltage sub 1. And we need to consider here the resistance and the current involved. So voltage sub 1 here is going to equal R sub 1 times I sub 3, all right? That is the current running through here. Okay, so V sub 3 for resistor sub 3 similarly is going to equal I sub 3 times R sub 3. And this, of course, is according to Ohm's law. Okay, so the sum of these two voltages should equal 3 volts according to Kirchhoff's law. So we then look at loop number 2. And loop number 2 gets a little bit more complicated because in addition to these voltages, which are going to remain the same, we have a voltage that has different current, okay? So in this case, V sub 2 is going to be equal to the current running through this part of the loop, which is, of course, I sub 2, and then times R sub 2, okay? So I just named these resistors with a subscript in a way that is convenient for me, but you may have a different idea of what's convenient. So if you do, name them what you want. The other thing I should note is that our current going into each junction, again, according to Kirchhoff's law, will equal the current going out of each junction. So in this case, I sub 1 plus I sub 2 will equal I sub 3, okay? The sum of current going into a junction must equal 0 is another way to express it. Okay, so now let's do the math. Once we've set this up, it's fairly straightforward. So here we have, as I described it earlier, V sub 1 and V sub 3. And so we have V sub 0 minus V sub 1 minus V sub 3 equals 0, okay? So we start plugging in values and we can solve for current. Now I looked at the solution in the test yourself answers folder, and it's a little bit different than the one I use. Either way is fine. In both cases we get to the same answer. Okay, so I find I sub 3 which is the current going through this middle part here. And when I finish I sub 3, when I finish that calculation, I will find that I sub 3 is equal to 0.06 amps. Okay, we then look at loop 2, and we go through the same process. Remember though that our current is not the same through one of our components. Okay, so that does complicate things a little bit, but since we know I sub 3, it actually doesn't complicate it that much. Okay, we can solve directly for I sub 2 in this case. And when we solve our equation, after plugging everything in, we will get negative 0.1 amps. Okay, so this is one of those times where, you know, loop direction is going to have an impact, right? We're deciding which way is positive and negative here. Okay, so finally, we need to find the current through A sub 1, ammeter 1, which we've not done yet. Okay, so I'm calling A sub 1 I sub 1 using the variable for current. Why isn't my pencil working? There we go. Okay, so so I is the variable for current, so that's why I'm doing that. I'm not trying to confuse you, I swear. Okay, so again, Kirchoff's law says the current going into a junction is equal to the current going out of the junction, or vice versa. So I set up my problem, I sub 3 is equal to I sub 1 plus I sub 2, and I solve for I sub 1, and plug in my values, and I get 0.16 amps. Again, this is exactly the same as the answer your book came up with, but they used a slightly different method, just a little bit different algebra, same answer. Okay, so next, potential differences. Yes, we're asked to find the potential difference across each resistor. And if we know the current, then this is quite straightforward, and this is actually another reason why approaching it this way is kind of an advantage, because you already know that current when you start this problem. So since we've already calculated the current across our center components there, all we have to do is plug in our values according to Ohm's law, and there are your answers. Very straightforward. I don't think I need to chat about it in any more detail than that. Okay, guys. If you have any questions, or girls, there may be females listening. I work for a boys' school, so I tend to assume that's not the case, but we are on the World Wide Web. Okay, anyone listening, if you have any questions, please do not hesitate to let me know, and have a fantastic day.